Hello everyone, my name is Prashant Vashish from BSc Chemistry on second year, and today we are going to study chapter transition elements. What are transition elements? The elements lying between S and P block of periodic table that constitute a large block of elements are called transition elements. These elements have partly filled n-1 d orbital since last electron fell into d orbital, so they are called transition elements or d block elements. They show transitional behavior. Transitional metals elements or D block elements. They are classified into 4 series 3D, 4D, 5D and 6D or 1, 2, 3 and 4 series. Each series has 10 elements while 60 series at present only one element namely actinium. Z is equal to 89. The elements of I group Cu, Ag and Au should not be included in D block because of their filled d orbital, and then CD, Hg are also have filled d orbitals except their formation of complex. These elements are much different from properties of next of the elements due to the periodic classification. These elements show a wide application such as in heavy industries, paint industries, catalytic use, building materials, jewelry items and coins. Biologically active compounds such as hemoglobin, myoglobin, proteins, synthetic oxygen carriers, vitamin B12 contain different transition elements. The elements of group 3rd, 4th, 5th, 6th, 7th, 8th and IV 3rd to 12 belong to this block. Position of elements in periodic table. These D block elements are placed into 4 series of 10 elements in each, which are kept in 4th period 3D series, 5th period 4D series, 6th period 50 series and 7th period 60 series in complete series. 4th period first transition series, 5th period second transition series, 6th period third transition series, 7th period fourth transition series. General characteristics of D block elements. All transition metals are hard except group 11, copper family, and have high melting point and boiling point. Nearly 10 transition elements have melting point above 2000 degrees Celsius, and 3 elements T, A, W, and Re have melting points above 3000 degrees Celsius. They are hard, strong, refractive, and electropositive. The transition elements all have high densities. OS and IR have densities of the order 23 gram per centimeter cube. Most of the transition elements are malleable and ductile. Most of the transition metals are good electrical conductors. Most of the elements form colored compounds of every color of the rainbow. They form along with other metals. These elements form well-known coordination complexes. Transition metals exhibit several oxidation states. Most of the transition metals and compounds are used as catalysts. The general properties of D block elements of all the series 3D, 4D, 5D, 6D are not so different because of this electronic configuration, which includes the number of electrons in d orbitals are generally same, only vary in number in s orbital. It is invariably 0, 1 or 2. Important physical properties of the elements discussed below and the data are given in table. This is the table important physical properties of transition 3D series elements. Properties. Electronic configuration of transition series elements. The electronic configuration of 4D and 5D series are given for comparison with 3D series. The outermost electronic configuration valence shells of the series can be represented by 3D 1 to 10 4s 1 to 2 table 1.1. First two electrons go into 4s orbital due to their low energy state compared to 3D orbital. Rest of electrons enter into 3D orbital. Since the filling of electrons takes place from 1 to 10 in d orbitals, these are called 3D series, 4D series, 5D series, and 6D series. There are certain exceptions in configuration of CR Z is equal to 24 and MO Z is equal to 42. The expected configuration of CR atom is argon 18 3D 4s2, but actual configuration of CR atomic number 24 Kr18 3d5 4s1. This can be explained on fact that these orbitals have close energy separation, thus giving rise to 6 nearly same energy state, and extra stable configuration is observed for both CR and MO as given above. In table 1.1, 1.2 and 1.3, two type electronic distribution are given given. One is represent predicted and another is observed. Observed is actual electronic configuration found by experiments. The irregularities found in observed configuration from predicted I are CRCU, MOPD, AG, and AU are explained on the basis of half-filled, completely filled d orbitals are relatively more stable than other d orbitals. On the basis of this concept, it is, however, not easy to explain the irregularities found in the other elements, since one has to consider net effect of so many other factors such as nuclear electron attraction, shielding of one electron by several other electrons, inter-electronic repulsive forces, exchange energy forces. All these forces play an important part together in determining the final stability of electronic distribution of atom. It is not easy to explain configuration of Nb, Ru, Rh and tungsten, unlike chromium 3d54s1 and molybdenum 4d5s1 should have idealized the configuration 4f14 5d46s2 electronic distribution of first series elements. Here, AR means electronic distribution of atomic number 18. The general electronic configuration of 3D series may be given as n minus 1 n minus 1 d1 to 10 ns1 to 2 n equal to 4. Electronic distribution of second transition series elements. Here KR means electronic distribution of atomic number 36. The distribution, the general electronic configuration of 4D series elements may be given as n minus 1 d1 to 10 ns 0 to 2 n is equal to 5. Electronic distribution of third transition series. Here XC means electronic distribution of atomic number 54. The general electronic configuration of 5D series elements may be given as n minus 1 d1 to 10 ns1 to 2 n is equal to 6. Melting and boiling points. The d block elements have very high melting and boiling points and melts above 900 due to completely filled elements. Orbital elements like Zn, Cd, and Hg do not form compound. The formation of covalent bond present in rest elements as it also accounts for having incomplete d orbital, atomic and ionic radii. These points may be noted from the data of table 1, as it is clear from the table A that the atomic and ionic radii show a gradual decrease in their values in any period. This is due to increase in nuclear charge. This tries to pull the electron clouds toward itself. That is, the attraction of electron towards nucleus increases. This increase in attraction leads to decrease in radii values across each period. There are, however, few exceptions. The atomic radii of the elements from chromium to copper are very close to one another. This is explained as further the addition of extra electrons screens the outer electron very effectively from the nuclear charge. Thus, screening effect increase considerably, considerably due to increase in atomic number, and hence there is a marginable increase in effective nuclear charge. Thus results a small change in atomic radii of the middle elements in any period. In particular series, the atomic radius attains the minimum value for elements of 8th group, that is 8, 9 and 10, and increases again towards the end of a series. This is explained in terms of force of repulsion among the added electrons, which dominate with attractive forces due to increased nuclear charge and results in expansion of electron cloud. On descending in the group, principal quantum number n increases and atomic size is expected to increase from top to bottom, but the increase are not same for all the members. The difference in radius of second and third series elements is very small as compared to the first and second series members. This is due to the lanthanide contraction. Here is the inclusion of 14 lanthanide elements between La and HF density. The transition elements show a high density compared to alkali and alkaline earth metals due to smaller size and increased nuclear charge and poor screening effect by the orbitals. The electron are attached more strongly towards the nucleus. This results a decrease in atomic volume of transition metals and there is an increase in density. It can be also seen in trend of the table that density increases from period 4 to 6 elements. The osmium and iridium with highest values 23 gram per centimeter cube and then decreases in a group. There is also an increase in density of elements. This increase in densities is due to small radii and closed packed structure of elements. The densities of the second series is nearly two times those of the second series elements due to the atomic masses because twice those of the first series elements. Ionization energy. There is a considerable increase ionization energy value from the left to right in the series table due to effective attraction of nuclear charge on the electrons. Upper usual of table 3 and for sure higher value of ionization energies of third series than the first and second series. It can be explained on the basis of good shielding of outermost electron due to the presence of 4f orbital in the third series elements. The outermost electrons are more exposed to nuclear charge and therefore it enhances the ionization energy of third series elements. Oxidation states. This is one of the peculiar properties of transition elements that the element exists in different stable oxidation state. Change in the oxidation state usually shown unit charge of Fe3 positive and Fe2 positive as compared to non-metals usually changed by 2 units. After calcium atomic number 28, the electronic configuration 1s2 2s2 2p6 3s2 3p6 4s2. The next 10 elements will have the electronic configuration started with the filling of 3d orbital from 1 to 10. This prevails exception in the case of Cr and Cu due to extra stability of their half-filled or completely filled configuration. These two electrons prefer to shift their 1 4s electron and 3d orbital. Therefore, the first element of first transition series have an oxidation number +2 when 2 4s electrons are engaged in bonding and +3 when addition of one 3d electron is involved in bonding. Thus, from titanium to chromium, a regular change in oxidation state takes place with a correlation between electronic structure and minimum and maximum oxidation state. Further, the highest oxidation state of these elements, all of the s and u electrons are used in bonding. After the 3d5 configuration, the tendency to show higher oxidation state decreases among the rest elements. Fe has a maximum +6 oxidation state and rhodium, the often two elements of their group contain oxidation state +8 due to their larger size. The oxidation state of these elements are shown in table 1.6. Table 1.4 different oxidation states of first transition elements. Copper has a stable, completely filled configuration. 1.3 shows +1 by losing one electron from 4s orbital, whereas Zn shows only one oxidation state plus this cell is completely filled. Following point may be noted from data 1. There is an increase in number of oxidation states in going from left to right in period. However, the elements towards middle of the series have more oxidation states than those towards the end of the series. The increase in the number of oxidation states in proceeding left to right in a period is due to readily availability of S and D electrons for binding. Maximum number of oxidation states is reached somewhere in the middle of the series. The relative stabilities of various oxidation states shown by the given oxidation state can be explained on the basic stability of D0, D5, D and D10. Electronic configuration, for example, T4 positive 3D04S0 is more stable than T3 positive 3D04S0 because of the presence of D0 orbital in Ti4 positive ion. Transition elements can form ionic bond in their lower oxidation state and a covalent bond in higher oxidation state. The acidic nature of metal, oxygen and metal chloride bond increases with increasing oxidation state. Magnetic properties. The substance when placed in a magnetic field shows a decrease or increase in the magnetic field of strength. If the external magnetic field is larger than applied field, the substance is called paramagnetic. Diamagnetic substance repelled by magnetic field of strength. The transition metal compounds are generally paramagnetic in nature due to having unpaired electrons in their d orbitals. FeCO and Ni are ferromagnetic in nature due to the large number of unpaired electrons. In these elements, alignments occur when these metals are magnetized and behave as permanent magnets. The magnetic property shown by majority of the compounds of transition metals. This arises due to the spin of electrons and orbital motion, which produce a spin moment and orbital moment respectively. Therefore, an interaction of spin magnetic moment and orbital magnetic moment continues to produce magnetic properties in an atom, ion, or molecules. The unit of magnetic moment expressed as for magneton pm for electronet is given by this formula, where E is charge of electron, h is equal to Planck's constant, c is the velocity of light, and m is equal to mass of the electron. A magnetic moment of a single electron is given by this, where s is equal to total spin quantum number of unpaired electrons. For a single electron is given by magnetic moment for an atom or ion or molecules containing more than one unpaired electron can be calculated by this formula. Color. Transition metal compounds are compared in contrast to S and P group elements. Properties of these and differentiate to main group element due to absorption of radiations in visible region of the spectrum. The transmitted light is colored with the complementary color. The light absorption of radiation takes place due to the electronic transition caused by the changes in the electronic energy. This is also called electronic spectra. The transition elements compounds show various color depend upon the oxidation state and nature of ligand surround the metal ion. Thus, an aqueous solution of titanium 3 compound is blue green color. This compound absorbs light at 493 nm, correspond to the blue green with complementary color of reddish violet color. The copper compounds appear reddish blue as it absorbs red region. The various colors are given in table first. Transition elements. Metal ions which contain completely filled d orbital like M and positive, Hg2 positive, Co positive, etc. are normally white. For example, Z and Cl2 is white. Catalytic properties of transition metal. Transition metals play an important role in catalytic activities for the several commercial synthesis of various organic as well as inorganic compounds. Hydrogenation of unsaturated compounds, nickel is used as catalyst. In Haber process of synthesis of ammonia, iron and molybdenum are used as catalysts. Manganese dioxide and vanadium pentoxide are used to catalyze the decomposition of H2O2 and SO2 to get O2 and SO3 respectively. Other metals like chromium, platinum, etc. are also used in different chemical reactions. Formation of complex compounds. The transition elements have a unique property to form complex salts due to the presence of vacant d orbitals to accept electrons from Lewis spaces groups which are capable of donate a pair of electrons. These groups are called ligands. Uh, the number of ligands coordinated to metal is called the formation number of metal ion. The ligand may be neutral groups as NH3 and ion as Cl negative or Cn negative, etc. FeCN6 4 negative and FeCN6 3 negative complex compounds are formed by donation of 6 pairs of electrons from Cn negative to Fe positive and Fe3 positive respectively. Reactivity. The reactivity towards other groups is found less for the transition metals, high ionization potential and smaller size. Thus, they have tendency to remain unreactive elements. Elements like platinum and gold do not react with air and are called noble metals. Binary compounds for the first transition series. The elements with the only one other element combined to form a binary compound. These are the simplest type of compound formed by the transition elements with a variety of Non-metals like oxygen, nitrogen, phosphorus, halogen, and carbon form binary compounds. In lower oxidation state, metals form simple salts and show electropositive character, whereas in higher oxidation state, oxides are formed and metals show more electropositive character. Oxides. Oxides of the elements of first transition series show by general formula as MO, M2O3, MO2, M2O5, and MO3. Their stability increases from scandium to zinc. It indicates that the elements from starting in the 3D series attain stable state due to reduced electrons, and this show their strong reducing nature. In these elements, Cr2 and V2 oxides are strong reducing agents. Copper and zinc do not show +3 oxidation state. The oxides are basic in the low oxidation state and basic in high oxidation state of the metal involved. Therefore, basicity decreases from left to right in the first series of elements. Amphoteric oxide are formed by the intermediate oxidation state of metal. The basic and amphoteric oxide when dissolved in acid forming hexa complex ions MH2O6 and positive. Ammo type oxides in each M2 positive metal ions, and each O2 negative ion is surrounded by 6 M2 positive ion have a NaCl type crystal structure. Iron form a non-stoichiometric oxides in which ratio of the metal to oxygen is not a whole number. All oxides are stable, very stable, and are insoluble in water or aqueous acid, except NO2 dissolves in acid to give NO two positive ions. Chromium trioxide is soluble in water, converting dichromate ion. 2CrO3 plus H2O is equal to H2CrO7. It is a strong oxidizing agent and oxidizes many organic compounds. The acid-base character of the first transition series oxide in different oxidation states are given in the following table. Hydrides. Almost all the hydrides of the first transition series form hydrides by the accumulation of hydrogen atom in their interstitial space. Such hydrides are called interstitial hydrides and show variable composition as in PiH 1.8, PDH 0.6, and NBH 0.7, etc. The MH bond cannot categorize as ionic or covalent. These are solid, metal-like appearance, brittle with magnetic and conducting properties. Carbides. The metal interact with carbon at high temperature, forming carbides. Apart from carbon, atoms like boron and nitrogen can occupy empty spaces between the atoms of these metals. Such compounds are called interstitial compounds and called as carbides, borides, and nitrides respectively. The carbon atom causes a distortion of space of metals like CrM, NFe, CO, and Ni due to less space in crystal lattice to occupy. This is the reason that is why they are highly reactive. The interstitial compounds are high melting and hard. These are used for making heat resistant material and cutting tools as well as kiln and gas turbines and jet engines. Binary compounds of the first transition series. Complexes with relative stability of oxidation state. Tendency of the elements to form complex compounds is directly related to their reduction potential. Further, the oxidation state of the elements is stabilized in accordance with its electronic configuration, such configuration D0, D5, and D10 possesses more oxidation state. From left to right in 3D series, stability of +2 oxidation state will increase from Sc to Zn. Thus, lower elements in +2 oxidation state V and C are show powerful reducing nature, while Cu and Zn do not behave such reducing agents. It is observed that from Sc to Cu, the stability of +3 oxidation state increases. That is why +3 oxidation state of Sc is very stable. Ti is also oxidized to Ti3 positive and is also oxidized to Ti4 positive. Mn2 positive is also unstable, whereas Fe3 positive is a state of stable oxidation state. Following point may be noted. Stability of complex compound decreases with increasing atomic number of central metal atom. Transition metal in high oxidation state from stable complexes with the small highly electronegative and basic ligands like F negative, Cl negative, NH3I, O6, 5 negative, PO6, 6 negative, etc. While these metal in slow oxidation state, example 1 was plus 1, 0, minus 1, give stable complexes Pi. Acid ligand like COCN negative, PCl3, C6, etc. The complex compound formed by the transition metals atoms in low oxidation state contain L-M coordination bond. When the transition metal conform complexes with same ligand in different oxidation state, the complex compound having the metal in the higher oxidation state is more stable. Example CO3 positive NH36. 3 positive is more stable than CO2 positive NH3 whole 6. Greater stability is due to the fact the metal contains higher energy, having higher charge has greater power to attract the lone pair of electron on the ligand. In other words, we can say that since the metal cation with high charge is smaller in size, it can attract the lone pair of electrons of the ligand more strongly and hence can give more stable complex ion. Coordination number Cn and geometry of complexes formed by the transition series elements. First transition elements show 0 to 12 coordination number but greater than 8 is not isolated and very rare. These compounds are formed by reaction of their respective metal salts and species like NH3, H2, etc. containing the lone pair electron called ligand or Lewis basis. The bonding between metal and ligands are explained by Werner coordination theory, suggesting two types of valency, primary and secondary valency. Now, the term primary valency is called oxidation instead of the metal, and secondary valency termed as coordination number. Thus, the coordination number is the number of ligands which surround the metal in a specific arrangement in space. This specific arrangement of ligands around metal ion adopt a definite shape to have a minimum electrostatic repulsion and maximum stability. The definite shape is termed as geometry of the complex compound. For example, in the compound CONH3 whole 6Cl2 metal ion CO positive is surrounded by 6 ammonia molecules form the coordination compound and the coordination number 6 and octahedral geometry. Metal Cu, Ag and Au form the complexes with coordination 2 and adopt a linear geometry. The examples of such coordination compounds are CuCl2, AgNH3 whole twice positive, AgCN2 negative and AuCN2 negative. In such cases, all the complexes are linear and involve completely filled d orbital d10 metal atom. Complexes with coordination number 3 are not very common. Examples HgI3 negative adopt a planar geometry having coordination 3. Other complexes which show coordination 3 are A2CN3, S2O, SCN, SI, Me3 whole twice 3. Complex compound with coordination number 4 can isolated from number of metals. These are usually adopted tetrahedral and pure planar geometry. Although both the complexes have same coordination number 4 but adopt different geometry because of steric and electronic factor. A tetrahedral geometry is more favored due to steric effect makes maximum distance between ligands and minimum repulsion. This can be also explained on the basis of strength of ligand and formation of hybrid orbitals of central metal atoms. Ni involves 4s and 4p orbital in NiCl4 equals 4, whereas 3d and 4s in NiCn4 negative complexes adopt a tetrahedral and square planar geometry respectively. Other complexes of square planar geometry are CuNH4 whole positive. Complexes with coordination number 1 relatively rare. Examples of 5 coordinated complexes are CuCl5O 3 negative, CuBr5 3 negative. Coordinated complexes adopt a trigonal bidimensional square pyramidal geometry. These complexes are not very stable. This can be prepared on the basis of the formation of a dimmer or dimmer of MoCl5 coordination number 6 bridging by chlorine atom between two MO metals. The most common coordination of transition metal complexes is 6, which adopt a regular or distorted octahedral geometry. Gonally distorted structure is obtained for ligands around metal atom. Results of elongating or contraction of the octahedral geometry. Examples of the octahedral complexes formed by transition metals are FeF6 3 negative, COH6 positive, MnCN6 3 negative, and SCF6 3 negative, etc. The geometry of various complexes in several Cn numbers are shown below. For example, Cn is equal to 2 linear geometry. Example, CuCl2, AuCN2 negative, and AgCN2 negative. Cn is equal to 3. Geometry planar of pyramidal. Example, K2CuCN3H2 and HCI3. Fourth, Cn is equal to 4. Geometry square planar and tetrahedral given in the above figure 1.0. Example, NiCN4 negative, NiCl4 negative, and NiBr4 negative. Cn is equal to 5. Trigonal bipyramidal and pyramidal. Example, CuCl5 3 negative, FeCO5 and Ni83P2Br3. Cn is equal to 6. Octahedral geometry given in the above figure 1.1. Example, K4Cn6 CONS3 6 3 positive. Cn is equal to 7. Pentagonal bipyramidal capped octahedron and capped trigonal prism. Example, ZRF7 3 negative, MOF7 negative, MF7 2 negative. M is equal to NBOT. C is equal to 8. Cube hexagonal bipyramidal bicapped trigonal prism bicapped trigonal antiprism. Example, MOCN8 3 negative, TAF8 3 negative, ZRC2044 all 4 negative, ZRAAC all 4. Cn is equal to 9. Tricapped trigonal prism. Example, REH92 negative.